So, good morning, everyone. So, let's have a quick recap about what we talked about in the last class. There we finished talking about the single cycle implementation of MIPS CPU, focusing on a subset of the instructions, which covers almost all the aspects of the CPU's data path and control. So, at the end, we discussed a little bit about the performance. So, then we saw that the load instruction act as the critical path for our single cycle CPU, where you have the instruction using instruction memory, then the register file, then the ALU, then the data memory, and again going back to the register file to write a result. So compared to all the other instructions, in the load word instruction uses the most resources and takes the most time. So the delay or the latency of the load word instruction determines the clock period of our single cycle CPU. And so we saw that the other instructions like arithmetic or branches, they take less time, and jump take even less time. So most of the instructions take less time compared to the load word instruction, but we can't optimize for that common case or the majority of the instructions, because everything has to be done within a single clock cycle, and we had to stick with the delay of the load word instruction to determine the clock period. So it goes against our design principle, making the common case fast. So that is the major disadvantage of having a single cycle implementation. So then, to improve performance, what we can do is to go for a multi-cycle implementation. In order to do that, we need to divide our data path into small segments or stages, and each stage can be completed within one clock cycle. And this new clock cycle is only a fraction of the original clock cycle time for the single cycle implementation. In the single cycle implementation, everything needs to happen within the single clock cycle. In the multi-cycle implementation, only the work for that stage needs to happen within that clock cycle. So we can have a smaller clock cycle. So how we can divide this, we can roughly say instruction fetching can be done in one clock cycle, register reading can be done in one clock cycle, ALU operations in another, memory access in another clock cycle, and register writing in another clock cycle. So divide the data path into 5 stages like that, and you can complete each in one clock cycle. So that clock cycle is a smaller clock cycle compared to the original clock cycle. Now, not all instructions will use all these stages, as we have seen before. Load instruction will use all 5 stages, whereas most other instructions will skip the memory access stage and use the register write if needed. So 4 stages for most instructions. And jump instruction will only use 2 stages to complete, because it's only manipulating the program counter. So the clock period is decided now by the slower stage instead of the slower instruction. So we have to adjust the work done in each stage so that each stage can be completed within roughly the same time. So your clock cycle will be maximally utilized. Each stage will utilize the maximum amount of time given by that small clock cycle. So that is the optimal way to decide this clock period. Divide the work between the 5 stages as evenly as possible. So in that scenario, instructions will only use the stages that it needs. But still, an instruction has to finish before the other instruction can start. So how can we improve performance even more? Using a technique called pipelining, that is, try to use our hardware resources in the CPU in parallel, utilize the hardware as maximally as possible. Don't let any hardware stay idle at any time. So that is the idea of parallel execution. So today we're going to talk about pipelining. But before we go into the technical details of the MIPS pipeline, we will talk about, we'll have a look at a simple example. So to understand this pipelining concept, of course. So this example is a laundry shop. Imagine that we are running a laundry shop. So there are people bring in their laundry loads to be washed and dried and ironed and packed. So we have one employee in the shop. And in this example, let's assume 4 customers, A, B, C, D, are bringing their laundry to be washed and dried and ironed, folded, all that. So from our side, the shop side, we will serve them on arrival basis. That is first come, first serve. Whoever comes first will be served first. Next one will have to wait until the first customer gets their job done. So you can see there's in this little chart, these 4 customers have brought their loads to be washed, laundried, and we start at 6 p.m. and each customer has to wait until the previous one finishes. So, and let's assume that in our shop we have one washing machine which should take 30 minutes to wash a load of clothes, and we have one dryer which should take another 30 minutes to dry a washed load of clothes. Then we have one folding station where our employee will spend 30 minutes to iron and fold the dried clothes. Once the ironing and folding is done, there is one packaging station in the shop where the same employee will go and spend another 30 minutes packaging this ironed and folded clothes, all the packaging the entire load into one big parcel, and the client can pick it up. Right, so that is what happens, and each step takes 30 minutes. That is our assumption. So in this chart, you can see that the washing takes 30 minutes from 6 p.m. for the first customer. Then the drying takes another 30 minutes. So it's 7 p.m. already. And the ironing and folding, another 30 minutes. Packaging, another 30 minutes. So it's 8 p.m. by the time the laundry load of the first customer is done. Then our employee can start on customer B, and we spend another 2 hours for customer B, and we spend another 2 hours for customer C, and another 2 hours for customer D. So by the time we can close the shop, it's 2 a.m. in the morning, right? Okay, so 2 hours per customer to complete the entire work, right? Now, so this is very similar to single cycle CPU, if you will, but then we have divided the workload into 4 even steps, right? Instead of just saying doing laundry, we have divided it into 4 even steps from washing, drying, folding, and packaging. So then this can be looked at as a multi-cycle CPU as well. Right, so we are spending 2 hours per customer. What if some customer doesn't need folding or packaging? If a customer comes and says, I only need to get the laundry washed and dried, I don't need it ironed, folded and packaged. So that is somewhat similar to our multi-cycle CPU, where not all instructions will use all stages. Load instruction uses all stages. Jump instruction only uses 2 stages, something like that. So it's very similar. So some customers may come and say, okay, I only want washing and drying to be done, right? So our employee doesn't have to spend half an hour folding and half an hour packing. So for such a customer, we are only spending 1 hour. So it's very similar to our multi-cycle CPU now. Okay, so how do we go and put our pipelining concept on this? This is right. So we get more people, we hire more employees for our shop and try to do work in parallel. Now, in the earlier scenario, when our employee was folding a load of laundry, the dryer was idle, the washer was idle, and the packaging station was idle. So the idea is, while say for example, while folding one load of clothes, use the washer and dryer for the next loads of clothes which are waiting, right? So cut down the waiting time. That is the idea of pipelining. So here you can see that once the washing of the first load is completed and the first load is put into the dryer for drying, we can start washing the second load, second customer's laundry load. We can start washing, right? So the washer and dryer are now working in parallel. And then once the washing is completed for the second customer and the drying is completed for the first customer, we can move on to folding the first load, drying the second load, B, and we can start washing the third load, C. Okay, so now 3 things are happening in parallel: folding, drying, and washing. So you can see that more people are needed to operate these machines or move things around, but everything is happening in parallel now, right? Okay, in the next or the fourth half an hour, our customer A's laundry is now being packed, customer B's laundry is now being folded, customer C's laundry goes into the dryer, and we can start customer B's laundry washing, right? So by this time, all 4 stations in our laundry shop are occupied. Everything is being used, maximally utilized. So when we go on to the next half an hour, that is 8 to 8:30, we have already finished customer A. We are packing customer B's clothes. We are folding customer C's clothes, and we are drying customer D's clothes, and we can start washing the next customer. If there is a customer E, we can start washing his laundry. So, right. So by the time you have started the 4th customer or the 4th laundry load, all our stations are occupied, and we say that the pipeline is full at that stage, and we refer to that stage as a steady state. So it's like, imagine it's like the like sending water through a pipe. That is how the term pipelining comes. So it's like a sending stream of water through a pipeline. So it takes a little time to fill the entire pipe, but once the pipeline is full, when one unit enters, right? When one unit enters, the earliest unit is put out of the pipeline, sent out of the pipeline. So it takes some time, right? Takes some time to fill the pipeline, and it's not as efficient at that stage. Then we are spending a certain amount of time to finish this laundry load, but we haven't finished anything yet. But after this point, every half an hour we can finish a laundry load, right? assuming that we have other laundry loads coming after this, every half an hour we can finish one laundry load, whereas in the single cycle or the non-pipeline version of our laundry shop, we are spending 2 hours per laundry load here, right? Every 2 hours we can finish a laundry load without using the pipelining concept. Right. So what is the speed up we are achieving in this particular example? In the original this non-pipeline version, we have spent 8 hours, right, to complete the 4 loads. In the pipeline version, we have spent 3.5 hours to complete the 4 loads. Right? So the speed up that we have gained is 8 divided by 3.5, which is 2.3. That includes the time that we spend to fill the pipeline, right? So at these stages, not all hardware or not all the stations in the laundry shop are utilized fully. But after this step, when we are in the steady state, all 4 stations are utilized fully, and we can complete one laundry load every half an hour. So that state, after everything is filled, after the pipeline is filled, we call it the steady state. We are in the steady state. So in the steady state, one job is finished every 30 minutes, every half an hour. So when we are in the steady state, if we ignore the time to fill the pipeline, in the steady state, the speed up is say if you have n loads or n instructions in our instruction analogy, or n loads of laundry, we are non-pipeline version will take 2 times n time, right? 2 hours per load and 2 times n for n loads. Then in the pipeline version, we are finishing a load every half an hour. So half n, 0.5 times n. That is the time we are spending per load. Pipeline, per load, non-pipeline. So the speed up we are getting is, it ends up as 4. Roughly 4 if we include the first 1.5 hours as well. So we had to include that in reality, but when we have a lot of laundry load or a lot of customers coming in, we can ignore the time to fill the load. That becomes a smaller and smaller fraction, becomes negligible. If the pipeline is filled for 99% of the time, our laundry shop is operated. So you can see that if all hardware or all stages are maximally utilized, the speed up that we can expect is equal to the number of stages. If we can divide our stations or the entire work of the laundry into more than 4 stages, if we can divide into 8 stages somehow, then we can expect an improvement of or a speed up of 8 times, right? Because we can then finish one load at an even smaller time window, in an even smaller time window. So one thing to note here is the actual time taken to complete the laundry for a single customer, it hasn't changed, right? It's still 2 hours here, just like it's 2 hours here. But when we consider the entire workload of multiple customers, we are spending less time. So the performance term or the measure that we use in this scenario is called throughput. Throughput is how often you finish one job. In this case, every 30 minutes, every half an hour, we can finish one job. And that measure is called throughput. Here, the throughput is how often do you finish? It's 1 every 2 hours. Here, 1 every 30 minutes. So throughput makes more sense to describe the pipelining, the performance of a pipeline, but the latency or the actual time taken per load is still the same. So note that difference. Okay, so what are we actually doing here? We are overlapping the execution of different workloads, right? And we try to maximally utilize the hardware that we have. In the laundry example, we try to utilize all the stations at any given time. Whereas here, at any given time, only one station is being utilized, right? So parallel use, so parallel execution, overlapping execution helps us improve the overall performance of our system. And in our CPU analogy of this concept is called instruction level parallelism. That is, you try to execute multiple instructions at the same time. So if these are instructions, A, B, C, D are instructions, at a given time, say at this time window, 4 instructions are being served at different stages at the same time, right? So parallel execution of multiple instructions at the same time, that is called instruction level parallelism. There are other levels of parallelism, as you know, thread level parallelism, where you have multiple programs, program level parallelism, application level parallelism, and so on. So instruction level parallelism is a very lower granularity happening inside the CPU microarchitecture. Right. Do you have any questions at this point? Okay. Let's proceed then. Right. So with the idea of pipelining clarified, let's have a look at the actual MIPS pipeline that we are dealing with. So you can define the pipeline in any way you want. So we'll have a look at one possible MIPS pipeline implementation. So the first thing is to divide our instructions execution into a number of stages. So we have 5 stages in this MIPS pipeline, or 5 steps. So first step is IF, or instruction fetch, where we use the up-to-date program counter, which points to the next instruction to be executed. Using that, we go to the instruction memory and fetch the next instruction to be executed. So that operation happens in this instruction fetch stage, which is the first stage in our pipeline. Second stage, ID, or instruction decode. We don't just have instruction decode, we have instruction decode as well as register read. So decoding, what do we do in decoding? We look at the opcode and decide what category of instruction this is, and based on that we decide what are the remaining bits in our instructions, how they are organized. And once we know that, we can go and read the register file. We know the register numbers or register addresses in the instruction, we go and read the register file. So both those operations are done in this stage. Why do we do that? Because we want to evenly distribute the workload between the 5 stages as much as possible. That is the way we can minimize the clock cycle time and utilize the hardware maximally. Right. So third stage is execution, instruction execution, where in logical or arithmetic or shifting type operations, we use the ALU to do a computation on operands and generate a result. Or else if it is a memory related instruction, we use the ALU to compute the address, add an offset to a given base address and compute the absolute address that we are trying to access. Then fourth stage is accessing memory. Once in a memory access instruction, once the address is calculated, we can go and access the memory. Accessing may be reading or writing. So fifth stage is write back. write the result back to the register. The result may be result from the instruction execution stage, which is in the case of arithmetic logic shifting type instructions, or else if it's a load instruction, the result is the output of the memory. So hope you remember there was that multiplexer which decides whether to write the output of the memory or the output of the ALU into the register file, right? So write backstage, the result is selected like that and written to a register. So we have 5 stages and we have divided the workload as evenly as possible between these 5 stages, right? So let's have a look at an example. Assume that times for each of these stages are like this. So register reading and writing. So these are absolute times. These are not clock cycle times. These are absolute times. Time for register reading or writing, let's assume, is 100 picoseconds. And for all the other stages or operations, we are spending 200 picoseconds. Each stage consumes 200 picoseconds, right? So let's compare the pipeline data path with the single cycle data path. Now, right, so instruction fetch takes 200 picoseconds for all the instructions, all types of instruction. Now, remember, this is a subset of instructions. We were looking at load word, store word, R type or R format, and branch if equal. So each instruction has to be fetched, and the time for the fetching stage is 200 picoseconds. And the absolute time consumed by the register reading, where each of these instructions will have a register read, it takes 100 picoseconds, and the ALU operation 200 picoseconds. Each of these instructions will use the ALU whether to compute an operand or perform a computation on operands to generate a result or to calculate an address. Then load word and store word will spend 200 picoseconds on memory access, and load word and R format instructions will spend 100 picoseconds on register writing. So the absolute time taken by each of the instructions are like this. As we know, the load word instruction, it uses all 5 stages, so 800 picoseconds. Store word doesn't have a register write or doesn't use the write back stage, so absolute time is 700 picoseconds for store word. R format instructions don't have memory access, so 600 picoseconds. Branch, we don't use the memory access, nor do we use the register write, so 500 picoseconds. So right now, assuming that, so this is, we know that the load word instruction is the one that uses all 5 stages and consumes the most time. So let's assume that we have a program that is constituted of only load word instructions, right? A program that is composed of only load word instructions. So load word from a particular address into register 1, particular address into register 2, another address into register 3, and if you will, can imagine other load word instructions coming after this. So the program consists only of load word instructions. So in the non-pipeline single cycle implementation, what is the total time that we are spending? $800 picoseconds per instruction, right? So per every instruction, per 800 picoseconds, we can finish one instruction, one load instruction, right? So you do the instruction fetching, register reading, ALU, data access, memory access, and register writing. So we assume that register writing and reading takes 100 picoseconds, whereas instruction fetch, ALU, data access can take 200 picoseconds, right? So 800 total. So every 800 picoseconds, we can finish one instruction. Then in the pipeline implementation, now we have to align our stages into separate clock cycles, right? We can't do one after the other in an absolute manner like this. Now register reading or writing takes less time, but still we have to utilize a full clock cycle for that task. So here in the pipelining, instruction fetch and register reading. The decoding is there also. It's a combinational logic and it will take a little time here. In this case, we have ignored that, we have neglected that. It's a very small time, but it can be done within this space left here. So instruction fetch, decode and read registers, do the ALU operation to calculate the address, go to the memory with that address and read the data, write that data into the register, right? So you can see that now our time, absolute time per instruction is a little bit more increased, right? Little bit more increased, but we can do operations in parallel now. While the first load word instruction is being decoded and registers are being read, we can fetch the next instruction, next load word. And while that goes into decoding and register reading stage, we can fetch the third instruction likewise, right? So in this way, we can finish one instruction every clock cycle, small clock cycle, where this clock cycle is now 200 picoseconds, right? So the throughput is one instruction every 200 picoseconds. We can finish one instruction every 200 picoseconds. Okay, so keep a note on the fact that we have left the space in register reading here, do the decoding and do the register reading, but in the WB stage or the write back stage, we do the register writing here. In the first half of the clock cycle, we do the register writing. In the second half of the clock cycle, we do the register reading. So keep that in mind. That will come into play in a little bit, in a little further. We'll see why that is important, right? So the pipelining improves performance, and performance we are defining as throughput. The absolute time is either the same or a little worse compared to single cycle. Per instruction, the absolute time taken is either the same or a little bit worse, but the throughput is massively increased, right? We have 5 stages. We can get, theoretically, if it's ideal, a 5-fold increase or speed up of 5, but you can see that the speed up is actually 4 in this case. It's because of these added spaces to distribute the workload. But if you really want to look at the real timing, you know that the decoding will take, the combination logic will take some time there as well, which is not accounted for in this 800 picoseconds. It's actually more than that. And if you want to go for a real computation, the difference is not exactly 4-fold, but somewhere between 4 and 5. So, but for the ease of understanding, the speed up is 4-fold in this case, and the throughput is increased 4 times, right? Okay. Right. So if all the stages are balanced, if the workload in all the stages are balanced, all stages take the same time, that is, right? Each stage utilizes the clock cycle fully. We have work to do in each stage for that entire clock cycle. In that case, the time between instructions, or the throughput in the pipeline setup, is the time between instruction in the non-pipeline setup divided by the number of stages, if it is absolutely evenly divided, if the workload is balanced, right? So the number of stages in the pipeline is the maximum throughput increase or maximum speed up that we can gain. But in reality, it's a little less than that, because it's not possible to divide the workload exactly evenly between these stages in real implementation. So if not balanced, the speed up is less, but still it's really good. So again, note that the latency, absolute time for each instruction, it does not decrease. It is either the same or a little bit increased in the pipeline setup. Do you have any questions at this point? I'll take that as a no. Right. Okay. So at the very beginning, when we discussed about the MIPS ISA, we noted certain differences, right, with the ARM architecture that we have looked at earlier. So the idea of MIPS is it was designed, the ISA itself was designed for a pipeline implementation. So the one of the characteristics is fixed instruction length, which is actually the same with ARM as well, because ARM has the pipeline implementation in mind as well. But certain facts in MIPS, certain characteristics in MIPS helps the pipeline implementation better. So all instructions are 32 bits, fixed 32 bits wide. So the fetching and decoding is simpler. It's easier to do the fetching in one cycle and do the decoding in one cycle. So if you have multiple instruction sizes, then you have to have, say, your bus width. The number of lines in the bus is not fully utilized every time, and the circuitry that handles the data that travels through these buses have to account for different instruction bits, how many bits to ignore in each case. And that means added combinational logic in instruction fetch as well as in instruction decode. If the width of the instruction, the size of the instruction is larger or smaller, some instructions are larger or smaller than the others, then you have to have additional combinational logic to handle all these different possible scenarios. Okay, there's a question from Shamit. Isn't that space adding was done to roughly equal the clock cycle rather than using that time to decode? Yes, the purpose is to equalize the clock cycle, but the decoding can either be done in the previous clock cycle with instruction fetching, or it can be done along with instruction register reading. So we do it with the register reading because we have enough space there, right? So we need to distribute the workload as evenly as possible. So we have space in the register reading stage. So we do the decoding there. The combinational logic will still take some time. Also, as we go further, you will notice, remember that I told you the register writing and reading are done in two different halves of the clock cycle. So synchronizing that is also very important. So you will realize that it's nearly impossible for us to do that in the same half of the clock cycle. So we have to leave some space. Register reading and writing has to be mutually exclusive of each other with respect to time. So yes, the space adding in the register reading stage was done to have the same clock cycle. We have to have the same clock cycle for each stage. Then we add the decoding time there as well, rather than pushing the decoding time into the fetch stage, because we have enough time in there to do the decoding. Right. I hope that answered the question. And somebody else is raising hand. You can ask the question. Who's raising the hand? I can't see anymore. Can you ask the question? Whoever that was raised the hand, that raised the hand earlier. I didn't see the name. Okay, right, no problem. Right. So, Chamit, I hope your issue is clarified. Is it? Would you have any further questions on it? Okay, right. Let's move on. Right. So yeah, the fixed instruction size helps the pipelining. Then few and regular instruction formats, right? We only have say 4 different instruction formats. We don't have a lot of instruction formats. That means the size of the opcode is smaller and you can make a decision on it faster, right? So the decoding can be done really quickly because you only need a very small size combination logic to decode the small opcode, and based on that do the register reading, right? So you can fit the decoding and register reading in one step without uh, making that the slowest stage in the pipeline. So, and having regular formats. So you remember that the register fields in our instructions are nearly almost always in the same spots. The destination registers or the source registers, the first 2 register operands, they are in the same places in the instruction. The bit ranges are the same. So the decoding circuitry becomes really simple, minimal as possible. And then the ALU operation is decided separately, right? So for instructions that need different ALU operations like arithmetic, logic, shifting instructions, we have this funct field or the function field separately. It's not part of the opcode. So the funct field is used by the control logic a little later than the opcode is used. Opcode is used earlier and the funct field is used later by a different part of the controller. So why it's done like that? Because the ALU operation happens in a clock cycle which comes a little later. So it is okay for that signal to be generated a little later than the other control signals which are decided based on the opcode, right? So that is why the funct field is split into a separate field rather than make it part of the opcode. If we include the funct field in the opcode, then we have to have many more opcode, different opcodes. So the field used for opcode becomes larger. That will eventually, consequently, complicate the decoding circuitry. So by splitting the funct field away, we have made the decoding circuitry very simple. We have a small opcode and a simple decoding circuitry, right? So this then helps the pipelining design as well. So the ISA itself was designed keeping in mind that the implementation will be a pipeline implementation. This ISA suits a pipeline implementation to get better performance out of pipeline implementation, dividing the workload evenly, right? So all these things, facts are considered when the ISA itself was designed, right? So then load store addressing, the way that we have used the addressing modes like register and offset added together, right? So we have expanded the address range by having having one value in the register and coming up with an offset and adding it to the value, right? So now this operation, the address computation, can be done in the ALU stage, the execution stage, and the memory access can be done in the fourth stage, right? So the design was done like that, keeping in mind that these two operations will happen at 2 different clock cycles. So MIPS is designed for pipelining, actually, not for a single cycle implementation. Right. Okay. So with the concept of pipelining established and having gotten a good idea about how the MIPS pipeline works, next thing we are going to discuss is hazard. Now, we saw how pipelining can give us a really good performance improvement, right? 4 times, 5 times improvement with 5-6 stages of execution. So with 5 stages of execution, we can get an improvement of performance between 4 to 5 times better, right? So, but pipelining isn't just rainbows and unicorns. There are issues there as well, right? When you try to do something in a pipeline manner, all this parallel execution and maximal utilization of hardware brings us some issues, some trouble. So hazards are situations that prevent starting the next instruction in the next cycle, right? So that is the essence of pipelining is you can start an instruction every clock cycle. Even though an instruction will take several clock cycles to complete, you can start an instruction every clock cycle and you can finish an instruction every clock cycle. That is how the throughput is increased. So, but in certain situations, there may be issues that prevent the next instruction from starting in the next cycle, right? So there are different types of hazards that can create situations like this. So one type of hazardous situation is structure hazards, where a required resource is busy, right? Maybe the register file is busy, or the ALU is busy, or the memory is busy. We'll have a look at them closely, right? If a required resource, a hardware resource is busy, then we say that there's a structure hazard. If the instruction fetch is prevented because the hardware resource is busy, that is a structure hazard. Then there are data hazards. Data hazards are when we need to wait for a previous instruction to complete its data reading or writing in order to do the data reading or writing for the next for a subsequent instruction. May not necessarily be just the next instruction, maybe even the following one as well. So if we do the current data reading or writing, there may be data corrupted. We may be reading wrong values. So we may be corrupting values for the future. So such situations are called data hazards. We can't fetch the next instruction because if we fetch the next instruction now, that might lead to data corruption, right? So that is a data hazard. So we know structure hazards, you know data hazards, and the third type are control hazards. That is, the decisions for certain control actions depend on the result of a previous instruction. We can imagine that these situations might happen in branch instruction, right? So the decision for control action to change the program counter, let's say, it depends on the result of a previous instruction or previous operation, previous stage of operation, but the result is not still available. So yeah, we have a control hazard and we can't fetch the next instruction, right? So these are the three main categories of hazard situations where we are prevented from bringing the next instruction in the next clock cycle. We had to wait for a clock cycle or more, one or more clock cycles, because there may be a hazard like this, a structure hazard or a data hazard or a control hazard. Now let's have a look at this more closely. Structure hazards, right? Okay, now a structure hazard is a conflict on resource usage, right? The hardware resource is busy for a previous instruction, so we can't use that same hardware for the current instruction, right? So in MIPS pipeline with a single memory device, assume a single memory device. Now in our implementations that we had a look at so far, we had an instruction memory. We assumed an instruction memory and a separate data memory, right? We didn't Assume that these two are the same thing. Assume that these two are the same thing now. If you only have a single memory device where you have your program, instructions, and data, then a structure hazard can occur. Say load store instructions require data access, right? So both these instructions, load and store, they require data access, reading and writing. So instruction fetch also require memory access, instruction memory access. So if these two are at the same memory device, if you have the data as well as the instructions in the same memory device, then you can't access that memory device in the same clock cycle for two different things. So that becomes a structure hazard. So just have a look at this, the same diagram that we had a look at earlier with our load instructions program consisting of only load instructions. Now every clock cycle we fetch a load instruction and do the subsequent execution of it. Now at this stage, once you get this third load instruction is fetched, the previous one was in the register reading stage, the one before was in the ALU or the address computation stage. Assume that you have a fourth load instruction coming after this one. Then what would happen? That instruction will need to be fetched during this clock cycle, this 200 picosecond clock cycle. Now in that clock cycle, we need to bring the next load word instruction, fetch the next load word instruction, as well as do the data access for the first load word instruction in the pipeline. So if the hardware is actually a single device, if the data and instructions are in the same device, then we can't do this access in parallel, right? So that is a structure hazard where the hardware resource is already utilized and we have to wait until the resource is released by the previous instruction in order to use it by the next instruction. So we can't fetch the next load word instruction here. So in such situations, we have to do a stall. We have to wait. We have to wait one clock cycle until the hardware is released. That is called a stall. We have to stall the CPU without bringing in a new instruction for that cycle. So when we have a situation like that, we say we are inserting a bubble into the pipeline. So that is very analogous to having, imagine the water running through our pipeline. Now, our pipeline is very efficient. One unit of water enters while the other previous unit of water exits from the pipeline. But now we are inserting an air bubble into the pipeline where the pipeline is not filled at that particular stage. So we are sending a bubble through the pipeline. That is not getting any use of the pipeline for one particular clock cycle. So we are inserting a bubble into the pipeline by not fetching an instruction in a particular clock cycle. So that bubble will propagate from the instruction fetch stage into the next register read, execution, memory access, and all stages, the bubble will propagate. So at every clock cycle, one particular hardware will be idle, and there'll be one clock cycle where we don't complete an instruction, right? So that is called a pipeline stall, or inserting a bubble into the pipeline, right? So in order to avoid this particular structure hazard, pipeline data paths need separate instruction and data memories. So we can do the instruction fetch while doing the data access for a previous instruction at the same time. So one way is to have two different memories, or another solution is to have one memory but use two instruction and data caches, one instruction cache and one data cache separately. right? So we haven't talked about cache memories yet. We will start talking about this in 2 weeks time. So we'll talk about that in more detail later, but one possible solution is to insert a separate instruction cache and a separate data cache in between your CPU and the memory, right? So that is one possible solution. So we'll have a look at that closely later. Right, so that is an example for a structure hazard. Now let's have a look at an example for a data hazard. Data hazard is where the if you bring the next instruction now, you might be corrupting data, right? Or you might be reading incorrect data, right? So just imagine now you have in your program, you have an add instruction, right? Add from a particular value, $T1. T1 is a label for a register, a particular register number. So add these two registers together and save the result in a register labeled as S0, right? Then add T3 and S0, the newly computed value, which is saved in register S0, and save the result in T2. Note that we are computing a value and putting it in a register, and right after that, we are trying to use that newly computed value. Let's see how these are executed. Right, in our pipeline, so this add instruction is being fetched one clock cycle. Next clock cycle, we decode the register numbers. First we decode the opcode, then we come up with the register numbers and do register reading. We read these two register values from the register file, and we go into the execution stage. ALU, we add the two operands together and come up with the result. And we are not using the memory access, right? In that stage, we are not using anything. And in the last clock cycle, we are writing the computed result of the ALU into the register file. Again, note, reading is done in the second half of the clock cycle, and writing is done on the first half of the clock cycle. So, right. Now, the register file will contain the newly computed value only at that point, right? Once the write back is completed. But our next instruction needs that value. Sub S0 T3 and put the result in T2. So when is that value actually available? At that clock cycle. But earliest possible is after this execution, after the execution is completed for that add instruction, right? The earliest possible that the result is available. So but in reality, the value is written into the register file in that clock cycle. Then the sub instruction can only read that value from the register file here after the write back is done, right? The write back is done on the first half clock cycle between these 800 and 1000 numbers, right? Within that clock cycle, in the first half, we do the writing. Once that writing is done in the second half of the clock cycle, you can do the register reading. And the correct value will be available. So we cannot fetch this sub instruction at this stage, right? Right after the add instruction, we can't fetch the sub instruction. If we do fetch the sub instruction here, we will be doing the ID or the instruction decode register reading here. And when we read the registers, this S0 will contain an old value, not the up-to-date value. So we will be reading an incorrect value if we fetch the instruction here. So we have to insert two bubbles so that when we actually fetch the sub instruction here, the correct value in the register named as S0 is available for us to read for this sub instruction, right? So that is a data hazard. Fetching the instruction here is a data hazard. So we have to stall the pipeline. We have to insert one bubble here and another bubble here, right? So two bubbles in the pipeline, one after the other. So you can only fetch the next subsequent instruction here without causing any issues. Right. Then to solve this to a certain extent, we can introduce a solution called forwarding or bypassing. That is, use the result when it is computed, not wait until it is stored in the register, right? So in order to make this function, in order for us to implement this, we need extra connections in the data paths, extra control logic and extra registers, a lot of different things. So we saw in the early example that the result of the add instruction is first available after this execution is completed, right? At that time, the result that goes into this S0 register is available. The number value is actually available. We only write it into the register during that half clock cycle. So we had to skip this memory access stage clock cycle. We had to wait, right? And then write it back in this half clock cycle. So in reality, the number is actually available here, but not available in the register file, available at the output of the ALU. So one thing we can do is let the sub instruction use that output of the ALU before it is written back to the register file for the input of the ALU in the sub instruction, right? So that is route the output of the ALU into the input, one operand, right? Route the output of the ALU into one of the inputs of the ALU. You need to use a multiplexer here with added control logic again, but that will allow the sub instruction to be fetched earlier. So let's have a look at that. Right. So here, add instruction has the result that goes into register S0 computed here, the sum of T0 and T1 available at that point in time. If we can forward that to the input of the ALU, input of the same ALU actually, the next instruction can use that in the next clock cycle. The ALU can use that in the next clock cycle for the sub instruction. So in that case, if we can add that functionality, then the sub instruction can actually be fetched right after the add instruction in the very next clock cycle. So we do the fetching, we do the instruction decoding, right? We do the instruction decoding, register file reading, but now instead of the register file value that we read for S0, we use this. We use the output of the ALU, which is the result of the previous instruction. So we use that. The write back will happen a little later and the register file will be updated in 2 clock cycles time, but we use that result earlier to support this next instruction. So that concept is called forwarding. And to implement forwarding, you don't wait until the value goes into the register file. You need extra logic, extra control logic, and extra registers to pass these values, and careful synchronization as well, right? So forwarding actually helps us avoid 2 bubbles in the pipeline. So that is actually a massive improvement. If we have to insert 2 bubbles in the pipeline, we are losing our performance a lot. We are wasting 2 clock cycles, whereas we are supposed to finish 1 instruction every clock cycle. Now we have saved those 2 clock cycles, and that is a major improvement, because there will be plenty of instances in your programs where you will be generating a result to a register and using that right after that. So such instances are common, and forwarding in the pipeline microarchitecture helps us save performance, or helps us not lose performance. Right. So that is all very good, but it doesn't actually work all the time. For certain data hazards, it doesn't work. That is like load and use, right? So load one value from the memory into a register and use that right afterwards. It doesn't really work. The forwarding solution doesn't really work for this to avoid the pipeline stall, because in a load instruction, the result is generated at the end of the memory access stage, right? So in a load word instruction, the result is available after the memory access stage is done. Now, if we want to fetch the next sub instruction right after this load word instruction, it will be using, the execution will be done here, right? This execution stage will be here if we have fetched this here. Instruction fetch, decode, and execute. The execution is done here. For the execution to be done there, the result should be available at least at that time, right? The result for this S0 should be available at least at that point in time. But the result is actually available first at that point in time. Still not in the registers, but at the output of the memory. So we can't forward backward in time. That doesn't make sense. That's a paradox. So we have to wait one clock cycle. We have to have one stall or one bubble in the pipeline, which cannot be avoided if you want to load a value and then use that value right afterwards in the next instruction. So a load use data hazard will always cause one pipeline stall. One unavoidable pipeline stall is caused by this load use hazard. If you have a load word instruction and a following instruction which uses the loaded value. Right, so any solutions for this? Not in the microarchitecture, but by the assembler. You can reorder your code to avoid use of loaded result right afterwards in the next instruction. So let's take an example, a simple C code, add B plus E, save it in variable A, add B plus F, save it in variable C, right? You use B there and you use B there, right? Okay, so let's have a look at the assembly for that. So here, load word, let's assume B, right? B into T1. Load word E into T2. Then add these two together. Add B and E together. Add T1 and T2 together to generate a result in T3 and store that in a certain address. So that is A, right? The result of add is A, and you need to store it in the memory where the variable is actually held. So load B, load E, add them together, save the result in memory. So these 4 steps or 4 assembly instructions account for this one statement in the C code. And you can see that we are using the T2 register value for E, let's say, the loaded value right afterwards for the add operation, right? So we will enforce a stall if we have the program like this. We have to have a stall between this load word and add instruction. Stall before this add instruction. We have to insert a bubble. And then once the value for A is stored, we are loading the value for F into register T4. We already have the value for B loaded in register T1. And once F is loaded, we need to add F and B together, right? Add the newly loaded F with the previously loaded B and generate the result for C and write that result into the memory where the variable C is located. So again, we have a load use data hazard here, and we are forcing a stall before this add instruction. So how many clock cycles will we spend, assuming that we finish one instruction every clock cycle? Load word, add, store word, load word, add, store word. So 1, 2, 3, 4, 5, 6, 7 instructions all together, plus 2 unavoidable stalls because of these two load use data hazards. Then 9 clock cycles altogether, right? We are spending 9 clock cycles for these two statements. Now we can go and reorder the instructions to avoid these two load use data hazards and still get the correct execution. So what we do is we load the three values one after the other. We load B into T1, we load E into T2, and we load F into T4. We do this loading of the value F from memory into register right after we do the loading of these two and before we do the adding, right? So what have we done there? We are going to do the loading of this F value from memory into a register in that bubble space in this situation, right? Where a bubble would have been enforced, where a stall would have been enforced in the pipeline. At that place, we are doing the load. We are actually doing some useful work at that space, whereas otherwise this would have been a stall. Now we are doing a load, which doesn't really break any structure in our program, right? So we can do the loading of F, then the add can be done, right? So one wait, and during that wait we load a useful value, and after that we do the computation of the previously loaded values, right? T2 can be used after one clock cycle by having the forwarding functionality, right? Even if we didn't have the forwarding functionality, we have to have two stalls, remember? So if we have forwarding, we can use it after one clock cycle. So in that one clock cycle wait, we have done some useful work. Now that load use hazard has been avoided now. Next, we do the store before we do the next addition, right? So in that, in the next load use hazard has already been avoided because we did the load earlier, and now we have waited 2 clock cycles actually, and we can do the addition because the result of this is now already in the register file. So we can, even without forwarding, we can do this add the instruction at this step. Now, how many cycles are we spending? We are spending only 7 clock cycle, one per instruction. Whereas here we spent 9 clock cycles, which included 2 pipeline stalls. So reordering your code can help avoid these load use data hazards and save our performance, not lose our performance. Right? So that is another technique, but this time it has to be done by the assembler. Assembler has to look at the code and arrange it properly to avoid these load use data hazards. So that is another task that an assembler, a good assembler, has to do. So just to give you another hint, so when you guys are looking at programming in other courses, keep these things in mind. So you have, your assembler should do these things for you, or else you have to go and look at the assembly code and figure out optimization for yourself if the assembler doesn't do it. So to get really good performing code, you need to be a good programmer, as well as you need the support of these other systems tools in order to get a really efficient program. Otherwise, you'll be wasting time like this, right? Unnecessary stalls in the pipeline will be wasting time, consuming, increasing the time consumption for your programs that you run. Okay. Any questions at this point? Yeah, I'll take that as a no. Right. Then the third type of hazards are control hazards. Right. So the branch instructions, you know, they are the ones that determine the flow of control, whether you need to fetch the next instruction in the sequence of execution, or you want to jump ahead in the program or jump backwards in the program, right? So the fetching of next instruction, it actually depends on the outcome of the branch instruction. When you have branch instruction in the pipeline, the instruction that should be fetched after that depends on the result of that branch instruction. You need to do a computation, a subtraction of two register variables, register operands, and based on that decide where to fetch the next instruction from. So pipeline can't always fetch the correct instruction if you if you have a branch instruction, right? Because you have to wait until the execution of that branch instruction is finished. So in the MIPS pipeline, we need to do either need to compare the registers, the values from the register file that need to be subtracted, and compute the branch target early in the pipeline without having to wait until the ALU computes this and ALU finish the execution. We can added hardware, we can add extra hardware to do that subtraction in the instruction decode stage itself. Read the registers and do the subtraction in the instruction decode stage itself. You can add another small combinational adder just to do that and get the result early. Decide whether if it's a BEQ instruction, decide whether the two operands were equal early without having to wait until the execution stage. We will get it done in the instruction decode stage by using a separate hardware to do that, only for the branch computations. So let's have an example. Right. So here we have we do this add the instruction and we do a branch instruction right afterwards. So the branch is subtract 2 from 1, and if they are if the two values are equal, then branch to a place 40 instructions ahead, right? Branch 40 instructions ahead in the program. So here we have to read these two registers 1 and 2 from the register file. If we fetch the branch instruction here, we will do the register reading, instruction decode and register reading here. The ALU is used to do the computation there to subtract 2 from 1 and generate the result. Based on that, we can go and do the modification in the program counter, update the program counter with the desired value, with either the PC plus 4 or PC plus 4 and align 40. So if we do it in the normal way, we have to wait until the ALU is done before we can modify the program counter and fetch the next instruction here. So if you have to do that, then we have to wait 2 clock cycles. We have to have 2 bubbles, so 2 stalls in the pipeline. If we use the ALU to compute the branch condition. If not, if we use added hardware at the instruction decode stage itself, right? This is the instruction decode register read stage. If we use an extra adder to do the subtraction of the register operands, then after this stage, at this stage, we can compute the branch condition. Based on that, use the instruction fetch circuitry to modify the program counter and have the next instruction fetched after 1 clock cycle. But there is no way you can bring the next instruction here. The next instruction based on the branch target here right after the branch instruction in the very next clock cycle, there's no way you can do that. Then you have to have 1 stall for every branch. So it's something unavoidable. If you have a branch, you have to have a stall in the pipeline coming afterwards, even if you have added extra hardware to do the branch condition computation in the register file reading or instruction decode stage. Right. Even in such situations, we can come up with some solutions like branch prediction. So these long pipelines, even long pipeline, you can't really determine the branch outcome early. You have to wait one clock cycle at least until the branch outcome is decided. So you are going to have a stall every time a branch is there. So one way out of it is to predict the outcome of the branch. You make a prediction, or you make a guess rather, whether the branch will be taken or not, and go with one case. If your prediction or if your guess was wrong, you have to go and do the stall. But if your guess is correct, you don't have the stall. So you can have a probabilistic advantage here. So we'll have a look at that. In MIPS pipeline, what we can do very simply is you can have a prediction saying that any branch will not be taken, right? Regardless of the two values in the branch instruction, the branch will not be taken. We can make an assumption or a prediction like that. And based on that assumption, let the instruction fetch mechanism bring the next instruction, that is with PC plus 4 increment, right? Bring the next instruction. Let the instruction fetch mechanism bring the next instruction and do the register reading for that. If our assumption was correct, we can get to know that earliest possible is after the instruction decode stage in the branch instruction. Then, if the prediction was correct, we have nothing to change. We can just let the brought instruction go into the execution stage. Otherwise, we have to discard that instruction that was just brought and fetch the instruction from the actual branch outcome which we predicted wrong, right? So here's an example. Here, what we're doing is a simple add instruction, right? Done, no issues. We have a branch instruction. If the values of registers 1 and 2 are equal, branch 40 instructions ahead. Ideally, or in the regular scenario, we have to wait one clock cycle, even if we have an extra adder in the instruction decode stage, to know the branch outcome at that time, right? We have to have one pipeline stall. But now, if we have a predict mechanism saying that this branch will not be taken, we are not going to branch 40 instructions ahead. If we make a prediction or a guess like that, we will let the instruction fetch mechanism fetch the next instruction using the PC plus 4 increment, the very next instruction after this branch in the program, right? So we assume that the branch will not be taken. We will go into the next instruction and we fetch that next instruction. And if our prediction was correct, right? This is a scenario where the prediction was correct. We have made a correct prediction. That is, in reality, these two values were not equal. So we are not going to make the jump or branch. We are only fetching the next instruction. And we have fetched it in the next clock cycle and we can let it proceed. Now, you can see here that at the time using an extra adder, we can know the outcome of the branch. We have only fetched the instruction. We haven't written anything into the register file. So we have not corrupted any data. So even if this was a wrong assumption, we have not corrupted any data. So it's not creating any issue. So if we don't have an adder here, and extra adder in the decode stage, we have to wait until the ALU is completed to know the outcome of the branch. And by that time, again, we haven't written anything to the register file. So we are not creating any issues. We are only reading, but we can simply have the control logic, discard all these values, and not let it go into the register writing stage. So having the prediction wrong will not give us a penalty, but having the prediction correct will give us an advantage of saving that one clock cycle. So here in this case, where the prediction was incorrect, we predicted the branch will not be taken. We wrote the load instruction here, but in reality, by that time, we know the branch will actually be taken. Even though we assume that it will not be taken, we guess that it will not be taken. In reality, it's taken. So we have to jump 40 instructions ahead. Now what we do is we update the program counter using the fetch circuitry and fetch the next instruction here. Now anything that had happened from there cannot be let to go forward, that load instruction. So the control logic should clear the values or set the control signals into this ALU and other registers, register file, data access, to make sure that you're not writing anything to the memory, you're not writing anything to the register file during those stages. So by doing that, we can have that one stall and jump to the correct target here in the next instruction. So what are we gaining here? If our prediction was correct, we are saving one clock cycle. If our prediction is incorrect, we are not losing anything. We would have lost this clock cycle anyway if we didn't have branch prediction. So we are not losing anything. So it's a good outcome for us, right? So if our prediction rate is better, meaning if our prediction is correct most of the time, then we can actually have this scenario more than that scenario. We can have the correct scenario more, meaning we are saving the clock cycle more often than losing that clock cycle. So there are different realistic branch prediction. Here what we did was we had a very static branch prediction saying the branch will not be taken. Every time we assume the branch will not be taken. So how can we make sense of that decision? So that is one type of static branch prediction, right? It's a fixed prediction, like we just saw. It's a fixed prediction. We always guess the branch is not taken. Branch will not be taken. So another type of static branch prediction we can do is base this decision or the prediction based on typical branch behaviors that we see in programs, right? So one example is in loop statements, the backward branch is nearly always taken, right? So if there's a loop that runs, say 1,000 times, for 1,000 times that backward branch will be taken. At the end of the loop, you check a condition and then you go to the beginning of the loop. It's a backward branch, right? So that will be taken 1,000 times. So more often than not, the branch is actually taken. Then in if condition, depend on the way you write the if condition, whether the true case or false case is written first. You can say that the we can predict for forward branches not to be taken, right? So, okay, you can analyze programs and come up with common behaviors like that. In loops, you can find backward branches and you can assume that those backward branches are taken more often than not. In if statements, depending on the way you write the if statement, you can assume that the forward branch, skipping something and jumping ahead branch, is not taken. You're not taking the forward branch. Instead, you're going to the instruction just afterwards. So based on that, you can make a prediction. So one such example is that, like this: predict backward branches always taken. We predict the forward branches always not taken. And if we can do an analysis and come up with the prediction like that, it might guarantee us that 90% of the time, let's say 90% of the time, the prediction is correct. Only 10% of the time prediction is not correct. And that is a very good outcome for us. 90% of the time we can save one clock cycle. So that has to be done by analyzing the programs quickly, carefully. And as programmers, you have to know how branch prediction is done and write your code based on that to get the advantage of these branch prediction mechanisms to again gain the best performance possible for your programs, right? So that is another thing to think about while you learn these microarchitectural concepts, right? Then that is static branch predictions. You get a fixed prediction based on a prior analysis. So dynamic branch prediction is where you have additional hardware in the microarchitecture which computes how the recent branches have been decided, whether the recent branches have been backward branches have been taken during the recent, say, 10 branch cycles. Last 10 branch operations, the backward branches, were they all taken? Were they mostly taken or mostly not? So things like that. So make the prediction dynamically in the runtime. The prediction is not made earlier. It's not a hard-coded prediction. The prediction is made in real time, in runtime, looking at the recently done instruction. So you can assume that, say, in a long loop, such a branch predict circuitry will note that you are seeing a lot of backward branches and they are always taken. And based on that, you make the prediction these backward branches are going to be taken. Next backward branch is going to be taken. So you can tune your branch predictor to the current piece of code that you're executing, current scenario you're dealing with, to get a better probability of your branch outcome. So likewise, there are a lot of different branch prediction mechanisms, very complex ones even, and I will actually give you some extra reading, an extra external reference to read for about these different branch prediction mechanisms, and certain things called out of order execution as well, which you will understand when you read. Okay, so next time we will go and look at the actual MIPS pipeline, look at how the hardware is used at different stages for these different instructions that we have taken as a subset: load word, store word, branch, and R-type instructions. So we'll have a detailed look into the pipeline in the next class, and I plan to stop here at this point. So if you have any questions, we can discuss. This is the time to ask questions if you have any. So today what we did was we talked mainly about the pipeline implementation and then the three types of hazard: structure, data, and control hazard situations, and what we can do to avoid these hazard situations or get around and still get the best possible performance. So we talked about different techniques and mechanisms. If you have any questions on that, we can discuss right now. Since no one has brought questions so far, I'll stop the recording now.